Yeah. So yeah, yesterday we finished recalling these facts about soft theorems. The fact that for very soft gravitational emissions, so graviton emissions from a given amplitude with some other hard particles, independently of how many gravitons you emit, the form to leading order is very simple. It's just the product of all the soft factors given by this formula, where Pj's are the hard particles, which, by the way, might be massive scalars like the ones that we discussed yesterday, but they can also be other types of particles. They can be fermions. They can be even other gravitons in particular. And okay, I hinted at the fact that the physical origin of this factorization, so the fact that each soft emission is independent of all the other ones, is a nice physical meaning, but then I forgot to say what the meaning was. Well, the meaning is that since the gravitons are very soft, it doesn't really matter how many you emitted, because you're never going to violate energy conservation, right? They are so soft that they have no impact on the induce no correlation in the other gravitons. And in fact, okay, I invite then, aside from this nice physical justification, I invite you to prove it on your own. Anyway, this factorization motivates us to introduce an operator, which I will denote in this way. Delta SR, which sort of stands for soft radiation, and I will spell it out as follows. There will be some WA dagger minus W star A, so that this is a manifestly unitary operator. The notation is the following: by integral over K and star, I mean the integral over the graviton phase space theta is the heaviside theta function, and then I put a cutoff because, of course, this exponentiation works very soft. This sort of factorization works for very soft radiation, so let me call it omega star, this cutoff. So for an integral for soft gravitons, essentially. And this WA dagger will be a shorthand for these contractions. So sum over the two physical polarizations of the graviton. W mu nu is the one appearing on this blackboard here on the left. And then let me call the polarization tensors, which you may choose, for instance, to be definite helicity states or cross and plus polarizations if you are more into gravitational waves. It doesn't really matter for us today. These are transverse traceless tensors, and I dagger is the creation operator. Similarly, of course, for W star A. And the creation and alienation operators, of course, obey the usual commutation relations that I'm sure you're all very familiar with. 2 pi to d minus 1 to absolute value of the frequency, say, of the momentum, say the one on the left, and then a delta function, k minus k. And then delta ij over the, let's say, the Wikipedic orthogonal polarizations. Very good. So the reason for introducing this operator is that then we can write this result for the factorization of soft emissions in a very compact way by, well, by, I mean, in an operator way. So the blob with all the soft emissions is just some expectation value if you introduce a vacuum that is annihilated, of course, by A. So the state with no gravitons. Then you can pull down as many soft factors as you want, I1, K1, A, I, N, Kn, from the operator sitting up there. Soft radiation, and then the blob without any soft gravitons. And then in principle I have to also divide by a normalization factor, which is the expectation value of this guy that I introduced. So this is an easy exercise in algebra of harmonic oscillators to show that this is equivalent exactly to this one. Now, actually I will not care about this normalization factor. This would be related to a point that I didn't actually raise yesterday. It would be related to an imaginary part that the iconal phase develops, but at higher loop orders, at higher PM orders. So for simplicity today, let me simply disregard this thing. The step that we are going to do, say, in addition to what Weinberg already did for us back in the days, is to do the Fourier transform of this formula. So I remind you that the Fourier transform introduced yesterday is a function of B. It is integral over the momentum transfer. So now we are essentially going to specialize to this background process being a 2-to-2 process, the one that we discussed yesterday, although the formula somehow straightforward generalized to more to higher multiplicity processes. P2 dot Q, e to the I B dot Q, f of Q. So we take the Fourier transform of both sides, and then what happens here is the following. So let me, since we are specializing to the 2-to-2 process, let me really erase and draw it like this. Now what happens is that here, the non-analytic dependence on the momentum transfer actually only occurs in the amplitude that we calculated yesterday at 3 level and also at 1 loop. And you remember, essentially we argued and to some extent checked also at 1 loop that this guy indeed exponentiates and gives rise to e to the 2I delta, what we call the iconal phase that encodes the information about the deflection angle, right, after taking this derivative. And now here, what I can write down as an operator that actually does this, let me strip the presence of these states and let me write this as an operator equation. Essentially what I get is that a good approximation for the S matrix, including not only the deflection but also the soft emission, is given by what we had yesterday, which is just the iconal phase, times this operator that I just introduced. In the sense that then taking matrix elements like above, you recover both the scattering process in the deflection process and the soft emissions. So let me somehow summarize what we learned and what is schematically encoded in this equation, that this guy is the elastic iconal. And encodes information about the deflection, theta for instance, and is the exponentiation of exchanges of gravitons, right? And instead this guy encodes the exponentiation of emissions. Now the only non-trivial bit in doing this Fourier transform is the fact that here, via this expression here, we remind you that P1 is equal to, say, P4 would be equal to Q minus P1, and P3 would be minus Q minus P2. If I specialize to the 2-to-2 process that I have on the right, there is still some dependence on Q, which remains in principle entangled in the Fourier transform. So what do I mean by this expression? Well, I simply mean that every time that you see Q in this object here, you can simply substitute it with minus I, the derivative with respect to B. Right, because of course in the Fourier transform you can use this. So this is legitimate every time the dependence here is analytic, and you can check that indeed if you expand this formula for small q, you don't get any 1 over q squared or logarithms of q, just some q squared to leading order actually. And so this is what I mean in this expression. Every time you would see q by substituting that formula over there, you just have to substitute the derivative with respect to b, but actually to leading order in the classical limit, this will actually be just the derivative of the iconal phase. The reason being that if you would, when you act with this operator on the exponential, the first thing that you do is indeed pull down derivative of 2 delta with respect to b, which is the classical impulse. Then when you act on the series, as you should be familiar from WKB methods, the leading order singular term, the leading order in 1 over h bar, let me spell it out, comes when you keep acting on the exponent, right? Instead of acting what you already pulled down, it would have less, you would have fewer powers of 1 over h bar, right? So in the classical limit, this actually becomes a factorization in which you simply substitute here the classical impulse. Is it somehow reasonable, right? An operator equation in the classical limit, factorizing it becomes just a product. Okay, so this is a bit schematic, but I hope the logic is clear. The elastic iconal encodes information about the exchanges, about the deflection. The, let's say, soft iconal operator that we plug in only encodes the fact that soft emissions exponentiate by what Weinberg told us. And what we are adding is that when going to impact parameter space and in the classical limits, the two factorize, and the only thing is that here you have to substitute the background classical process 2 to 2 with the classical impulse. So P2 is equal now, let's say, big Q, the classical impulse here and here. Very good. So now that we have this tool that, I mean, yesterday we were doing something not completely physical, right? Because essentially we were approximating the S matrix just by a phase, which means that we were saying that the 2 to 2 process was everything there was, and the final state would differ by initial one just by a phase shift. Now what we're doing today is a bit more physical because we're saying, okay, come on, there is a phase shift, but then there are also essentially a coherent superposition of graviton emission. So now we are in a position to calculate more observables, and the strategy to do that is to, okay, following in particular an approach that was introduced in this field by Kosover, maybe and O'Connell. Well, it's just to take expectation values. For instance, if I'm interested in some observable O, I will take now this expectation value, and in the classical limit, this will provide me with a prediction for this observable associated to this classical scattering process and the associated soft radiation. Of course, the drawback, I mean, this experimentation is very general, but the drawback is that it only applies for frequencies smaller than omega star, so very soft. So now, what I'm going to do is, in the rest of this lecture, is to apply this formula to some observables of interest and see what we get. So the first thing would be the gravitational field. So essentially, I'm going to specialize this O to being the canonically quantized graviton field. In principle, like I can put a star or not put a star here anyway. In the expectation value, I will only get the soft part. This guy here. And okay, one thing that we should recall in order to get our normalization factor correctly is that the metric fluctuation, the dimensionless metric fluctuation, which I might call H, is not just the expectation value of this guy, but it's actually square root of 32 pi g, the expectation of the canonically quantized, so canonically normalized in particular field, right? This is just, you know, the factor I have to put in order to go from the Einstein-Hilbert Lagrangian with the 1 over 16 pi g, I never remember, 32 pi g in front, to the one in which you have the canonically normalized kinetic term with plus 1/2 q dot squared, etc., etc. So this is dimensionless. And as you can see, what we are instructed to do is instructed to put this expression here inside the expectation value, which carries this S, okay, let me call it S soft radiation, because as I said, it's just, I mean, our description is accurate only insofar as we are considering soft emissions. So basically, the ingredient that we have to manipulate is the expectation value of this AI, right? Say the annihilation operator. Let me write it down once in its full glory. E to the minus integral of A dagger W minus A W star AI K E to the plus A dagger W minus A W star E to the plus. Okay, now I also put the elastic iconal just to remind you once again that its presence is not completely trivial. Now, of course, I will cancel it out, But we should remember that it was very important in order to get in W the classical impulse, right? Otherwise, we wouldn't know what to put inside this general expression that Weinberg gave us. Very well. Now it's an exercise again in oscillator algebra. So, for instance, a useful formula for doing this, let me remind you, is this one, which is one version of the Baker-Campbell, whatever. Which is just a shorthand for the commutator, because the commutator has this problem that it has these brackets, and then if you want to exponentiate it, you don't know exactly how to write it. So you introduce another notation. It just means you take all the commutators with the 1 over n factorial in front, and this in this case is very simple because this exponential actually truncates. You just have 1 plus the commutator between the exponent and b, because the commutation relation between a and a dagger is a C number. So of course, this should be very simple, and the outcome is that in practice each A pulls down an A dagger and vice versa, right? So what happens is that here I put A, this will pull down the coefficient of A dagger in the exponent. Yeah, maybe this is more efficient. And just to get the normalization correct, so h mu nu divided by 32 pi g. Well, no, okay, if I call it like that, it should be exactly h mu nu. We simply get, okay, the only slight subtlety, let's say, is what happens with the polarizations, right? In principle, you have a polarization both downstairs, let's say, and one inside the Weinberg factor. I mean, the Econol operator right there. So you will get a sum over physical polarization. Rho sigma. Let me put it in square brackets. E to the I k dot x, and then out of laziness, let me put plus complex conjugate. Now here comes this formula that I hinted at yesterday at some point. This guy is actually equal. You can prove it very generally to a simple combination. So let me introduce a notation for this guy here, for the TT projector. And the TT projector can be defined in terms of maybe a bit more precise than yesterday, where lambda is just a reference vector that satisfies this and this. So this is just the transverse projector. Now to build the TT projector, you have to subtract the trace as well. Something like this. So in the rest, I will just use this TT subscript to denote this rather cumbersome thing of saying you contract with the TT projector, and then the free indices are the ones sitting in the projector. And this brings me to, well, to the final formula. So basically, we learned that we have to do a Fourier transform of the Weinberg factor. In the very end, it's nothing more than that. In principle, I should keep putting a star here, right? Because, of course, the commutation relation, when it pulls down this guy from up there, it remembers that due to the delta function, it will be non-zero only when the frequency is smaller than omega star. Now, what we did is a bit, well, it should sound a little bit fishy, right? Because this is the expectation value of the gravitational field in principle anywhere. It just depends on x. Whereas, of course, we know that whatever we get out from amplitudes, in particular from the 2 plus n gravitons, will only be reliable away from where the scattering actually happens, right? Because it must be in the weak field regime. So maybe I can. there is this blackboard and discuss this point here. Well, in order to do that, we have to do the limit that Andrea was doing in all his lectures. So we have to evaluate this field far away from where the scattering happens and, okay, following the outgoing radiation towards null infinity, right? So now we're going to go to Scri plus, which means that, okay, let me introduce some notation. X mu for us is going to be now u, the retarded time, times some vector t mu, which for instance you could take to be 1, 0, 0, 0 in some of your preferred reference frame, plus r, which is the radial coordinate, times n mu, which is a null vector, which encodes the angular direction in which you're going away from the source, which you can think as 1, n hat being a unit vector, right? This is just a bit more covariant because then you can choose whatever observer you want as long as you impose n dot t equal to -1. And then what you are going to do is we're going to evaluate this formula for large R at fixed u and n. Okay? So, okay, to do that, well, I wanted to do this in slightly more general way. Let me just consider some expression like this. Okay. E to the I k dot x. So this is just more generally analyzing something that is evaluated on the mass shell of a graviton, and we are going to evaluate its asymptotic limit to Scri plus. So one can do this in several ways. One way is to change variables. So k mu, which is our integration variable, let me remind you that, well, maybe I can rewrite it here. Integral over k is a shorthand for integral over d k divided by 2 pi, delta of k squared, 2 pi, theta of k0, and, well, that should be it, right? Yeah. And, okay, we can change variable, for instance, called rho t mu, in a way similar to what we did for the spatial coordinate, for the space-time coordinate, plus, let me call it omega m mu, where now m is a vector that satisfies more or less the same thing that n did. Nt is equal to -1, and m squared is also 0. So then we get that dk is d rho. So t instead is constant, right? So t mu plus d omega m mu plus omega dm mu. And then dk squared, which is the thing that will, from which we can derive the Jacobian for this transformation, is just the square of this. And using these two relations, you can of course see very, very easily that, for instance, dm dot t is 0 and m dot dm is also 0. So you get minus d rho squared plus 2 d rho d omega. And then the only thing that you can do is omega squared dm squared. So from this we see that the Jacobian follows this way. Of course, here I put, sorry, maybe let me spell it out more clearly here. Here I put theta of k0, and this could, sometimes could induce in you the suspicion that this formula is not actually covariant, right? Because k0 with respect to whom. But as long as we are on the light cone, it doesn't matter. You can choose any time-like vector. For instance, I can choose t, which is my preferred one. And then you should be able to get this. So this is the, delta squared and the theta 0 or theta minus t dot k that comes from the measure. And from this you get the Jacobian, which is as follows. Maybe I can erase up there. So in taking the Jacobian, you have to remember that dm squared is actually the metric on a d minus 2-dimensional surface, right? Because it satisfies two constraints, m dot t equal to -1 and m squared equal to 0. It's basically a section of the light cone written in some slightly more general way. Well, I actually had left the thing here, sorry. I can use it. So integral become from 0 to infinity thanks to the theta function, d omega, and then the 2 omega also comes from the delta function. And then you have this, let's say, d minus 2m, which is the measure on this. I mean, it's essentially a sphere, although I'm not spelling it out very maybe in a sort of unfamiliar way. And then phi tilde of omega m, because as you can see, the delta function sets rho to 0. I mean, the time, let's say the component along T mu, omega m, times e to the I omega u plus I omega r n dot m. This is in fact the important part. So now you see what we want to, so up to now is just a change of, a change of variables that puts the integral in this form. Now what happens is that when we are sending r to infinity, this integral could oscillate very rapidly, right? Unless, for instance, n is very close to m. N and m are both null vectors, so if n tends to m tends to n, this thing goes to 0, so there is a chance that the oscillations cancel out. So this is what we are going to focus on. We are going to focus on this sort of collinear region. You can think of this as an application of the method of region, in which we say that m is essentially, is n plus z, and z itself is small. Let's say it's of order 1 over r, right? In order to, sorry, square root of r, in order to compensate for this r squared. Maybe in order to understand why, you need to remember that in order to satisfy this constraint here, m dot t equal to -1 and m squared equal to 0, we need to have that z dot t is 0, so it's a spatial vector, and also -2z dot m is equal to z squared, right? So this is why I'm saying it should be of order 1 over square root of r. Should be more clear, hopefully, once I write down the next. After doing this change of coordinate, yet another change of coordinate to omega m. So basically what you see here, in principle, I should put n plus z, right? But since z is very small in this region we are considering, I'm going to neglect this. And then I have the integral over z that comes from the integral over m right there. And what we are left is e to the minus I half from the last term using this identity here, omega r z squared. So now you see why I sort of guessed this 1 over square root of r in such a way that this exponent is doesn't scale, right? Very good. Now the benefit of doing this is that the integral has become Gaussian. It's just a two-dimensional Gaussian integral that you can do. And the result is the following. Let's say limit ascribe plus is d omega over 2 omega. Omega to d minus, well, maybe let me pull out some pi's and related things that come from the Gaussian integration. Integral from 0 to infinity, d omega over 2 pi, omega to the d minus 4 over 2, phi tilde of omega n times e to the minus I omega u. So now essentially this is a rather straightforward way to see that any solution of the wave equation, right, because this guy is on shell, so it's phi box phi equal to 0, has a portion of its scaling that goes like 1 over r to d minus 2 over 2 in any dimension. Now, of course, we're going to specify to d equal 4 because we mean to simplify matters essentially. We can apply this to the formula that we got up there for the metric fluctuation, and this lands us on the following: h mu nu, so the waveform, sometimes also called ascribe plus. Now, okay, let me not do the math of these factors right in front of you because I will not get it right, but the thing boils down to a 4g over r integral from 0 to infinity d omega over 2I pi. The I comes from here. And then w tt, transverse traceless projection of the Weinberg factor e to the minus I omega u. And now to see the crucial point about this limit is that what we had started out as the direction of observation, right? This is where you actually place your detector at null infinity. in these angular directions here actually becomes the direction where you put your, let's say, your photon or your graviton in the integral. And then in principle, I should write plus compress conjugate. But actually, thanks to the property of this W, which I can probably write here. So W by the fact that 1 over P dot K minus I0 star is equal to minus P dot minus K minus I0. It's easy to see that then W transverse traceless satisfies that doing the star is equivalent to changing the sign of K. And therefore, I can actually combine the two integrals from 0 to infinity of W plus the other integral from 0 to infinity of W star, in which I had changed also this guy into one integral from minus infinity to infinity. Yeah, so this is the thing that we need to evaluate if we want to get the explicit expression for the asymptotic waveform in the soft limit. And, well, let's do it. By the way, this derivation is actually rather general. It doesn't really rely on the fact that we are focusing on soft radiation, in the sense that these properties, I mean, this property here and this property here are also valid, for instance, for the leading order waveform beyond the soft limit, but to leading order in the PM approximation. The reason why I'm not presenting that is that I cannot write it down on the blackboard. But it satisfies the same properties, actually. This is just an aside comment. So, okay, we need to evaluate this integral here. So it's an integral over the frequency of something that is dictated by the form of the Weinberg factor. So, as you might have guessed, is we have an I pi here and an integral from minus infinity to infinity. We are going to do this with residues. The reason, and therefore I need to be a bit careful about the sign of the momenta that enter the Weinberg factor, which I remind you is this guy here. Maybe J, Pj mu, Pj nu, divided by Pj dot k minus I0. So, you remember I have this convention in which all the PIs are regarded as outgoing, but this actually means that some of them are really physical outgoing momenta, some of them are minus the physical ingoing momenta. So to distinguish from, in the two cases, let me introduce a symbol, eta, which Weinberg also introduced, so we are not doing nothing new today, essentially, which is +1 if n is outgoing, and -1 if n is ingoing. And in this way you can, okay, restore the physical momenta just by writing eta n, let's say kn, for instance. Now kn are physical momenta in the sense that, for instance, their energies are positive, right? So these are really some En, Kn vector, and this guy is bigger than 0. So now you will understand momentarily why it's worth going through this trouble of being precise. Well, let me do the Fourier transform of one of these, right? Let me not do it for all j's. So we have to do the integral from minus infinity to plus infinity d omega over 2 pi I e to the minus I omega u 1 over pi or pj dot k minus I0, in which k is omega n, right? So, using this notation, and remembering that we are in the mostly plus, so for instance, kn dot n or kj dot n is negative, or if you want, this is positive, right? What we can do is we can pull out something positive from the denominator as long as we don't spoil the sign of the I epsilon. That is why I have to be careful about this. So we can rewrite this in this fashion, 1 over minus kn or kj dot n, integral from minus infinity to plus infinity d omega over 2 pi e to the minus I omega u, and then minus eta n or eta j omega minus I0. Right, so I substituted this definition and then multiplied it and divided by -1 if you want, to multiply it by -1 squared. So in order not to get a headache from doing the contour integration in several different ways depending on the sign of eta, let let me change variable to omega minus I omega, which we can do because the integral is anyway from minus infinity to plus infinity. D omega over 2 pi eta e to the I eta n omega u divided by omega minus I0. Okay. Now we are in business. Now this is the, sorry, I forgot the I somewhere in the meantime. Okay, now this integral we can do by residues, right? The trick is that when whatever multiplies omega is positive, then you can close the contour in the upper half plane, and this way you pick up the pole that sits here. Instead, when this guy here is negative, you have to close the contour in the lower half plane, and this way you miss the pole that sits here, right? And therefore, this integral is the theta function. So it's the theta function of eta n u. And then I forgot the 1 over minus kj dot n, and I realize now that I've been oscillating a little bit in what I used for j and n. Apologies for that. Eta j, eta j. Right, this is essentially an exercise in contour integration. So basically it means that this integral is 0 for positive u if the particle is incoming, 1 for positive u if this is outgoing, and vice versa for negative u's, right? So putting this all together, let me write the final formula, maybe somewhere around here. Yes, so let me write both the frequency domain and the time domain expression that we get. It's 4g over r integral, okay, keeping, let's say, the integral like we had it before, just making a bit more explicit, sum pn, okay, let me keep using j, transverse traceless divided by pj dot n, or pj dot, okay, omega minus I0. This is one representation in frequency domain, and then what we get by applying the formula that we proved in the blackboard above is that we get 4g over r. Let me differentiate by incoming and outgoing, otherwise it becomes a bit unreadable. We get the theta of plus u, so something that is non-zero for positive u, positive retarded time, sum over all the outgoing particles of pj transverse traceless divided by pj dot n, sorry, ej minus n hat dot kj, because I pulled out that eta and defined e and k in the way over there, plus theta of minus u, the same thing but with the sum over the incoming. Okay, I denoted it this way, transverse traceless ej minus n dot kj. Yes. So by the way, one thing that you should have complained about is that at some point I dropped the star from the integral. Of course, this is a minor sin, let's say, as long as we are looking at integrals for large u, right? Because you know that in Fourier transform, if you look at large u, it means that only the small omega behavior of the integral matters. So basically what this formula means, it's not really that it's a theta function in the sense that it really does a sharp step. It means that the behavior for large positive u is given by this expression, and the behavior for large, absolute value large negative u is given by this other piece of the formula. So essentially, this fixes for us the value of, let's say, hij, or the shear, or whatever. Let's say some combination of the shear as a function of u to be something like this, where here the value, the asymptotic value in the far past is given by, let me call this guy sum over in and this guy is sorry, out and in. Otherwise, I mean, I cannot copy all of them. This guy is given by some in, and this is given by some out. Okay, so this formula is one step away from the so-called memory effect. So now what we do is that we can evaluate the difference between the asymptotic value in the far future and the asymptotic value in the far past. So essentially h mu nu at u tends to plus infinity minus, which is simply given by 4g r, and as you can see, it becomes independent of u, because this thing is non-zero. Only this thing is non-zero for large positive u, and then we get minus, so sum out minus sum in. This is the so-called memory effect. And I mean, essentially should be intuitive, since this means that there is a permanent change in the metric fluctuation, which is what fixes the proper distance between let's say, the two mirrors in your interferometry experiment. This actually reflects in an observable effect. It means that the distance between the two mirrors will change permanently a little bit, as given by this formula. And okay, the next thing was to make contact with what Andrea told you yesterday, to show the relation between this expression and super translations. So maybe, by the way, interrupt me at any time if there are questions, as usual. Unless your spirit has been completely broken by Ellie's lecture. Esci from it, yeah.
So you mentioned distances with a given metric. Okay. If you change coordinates, normally the metric changes, the distance changes. But this is a mistake. This is just. So what is that makes this coordinate change a physical effect?
Well, this is
just changing coordinates and maybe scaling the distances and having a different number.
Well, I wouldn't say that this is really a coordinate change, right? I mean, I'm still using the same coordinates. It's really been a change in the metric itself. So, okay, then you can say you can mimic it, you can gauge it away in some way.
I mean,
yeah.
No, I think no.
No, no.
I would like you to go.
Exactly. So I think the answer to that should become evident once I remind a bit, recall a bit the super translation. Essentially, the reason is that this change depends on you. I mean, the form of this metric depends on you. What you can do using super translations, for instance, is to do a U-independent change, but this will not this will not change the difference between sigma out and sigma in. It will essentially just lower or raise the U-axis. So this is something that you might ascribe to a change of super translation frame. This will be the punchline, but the difference you cannot. And even the change of super translation frame, although it comes from general coordinate transformation, and then you might say it's part of the redundancies of symmetry, as we will see probably if we make it at the end of the lecture, actually has a consequence in the angular momentum spectrum. Yeah.
I guess this is what makes people confused about.
No, exactly. So this is. No, exactly. So of course you can say, I mean, as I will show now, you can always do some coordinate changes, and for instance, the super translations are the ones that Andrea showed preserve the fall-offs and still are non-trivial, etc., etc. And but we will see that we cannot super translate away this effect essentially. Very well. So let me do a very quick reminder. Yeah. Because I pretended it doesn't exist. In principle, it would.
It works like the scalar.
Yeah. So.
The I shouldn't.
Yeah. Okay. So what Matteo is pointing out is that in principle, when I did the trick of restricting to n very close to m, I was saying because otherwise this exponent oscillates very rapidly, and therefore I have to do something about that. Of course. The other option, instead of saying that z is small, would be to say that omega is small. That you can also do. However, by expanding for small omega, what happens is that okay, I forgot I need to do minus I omega here, sorry. What happens is that if you expand for small omega, this exponential will be expanded out, so you will lose the dependent on retarded time. So you might get some effect, which is again independent of you and therefore does not affect the memory effect. It could affect the precise value of the this sigma out and sigma in separately, and this is something that I think is not really understood. I mean, explained in the literature somehow. So, good point. Yeah, very well. So the action of a super translation was something like, remember that there is the metric fluctuation, which roughly speaking takes the form I wrote down sometime yesterday during the Q&A, essentially HAA or AB, which, I mean, the connection to what I was calling H mu nu is the following. REA mu, REA nu, H mu nu, where now I'm using this vector n hat that I had somewhere. So my n mu is 1 comma n hat, and then you can use this n to embed the sphere inside the flat space, right? So you can define EA mu as dxa, say, n, or just for short, dA. And these are the tangent vectors to the sphere, and the metric on the sphere that we're calling gamma AB, like Andrea did, is simply EA dot EB, or E mu, right? So this guy here changes under super translations as follows. There is R, so R is overall essentially H mu nu for me scales like 1 over R in Cartesian coordinates, but when you multiply by R squared it becomes order R, right? And then there is this change. T is a generic function of the angles, or of n if you would like, minus, let's say 2. Then I will forget about this factor of 2, because of course if t is an arbitrary function, 1/2 of t is also an arbitrary function. And this guy, Laplacian, is just the covariant, and d is the covariant derivative on the sphere, and the Laplacian is just dA. And then I have to close square bracket. So this is the variation of the metric under super translations, and if you are in a region in which the waveform or the and okay, HAB itself was something like RCAB, right? So it basically is a change of CAB. One change which is somehow obvious is the change under TDU, so the translation long time. But if you are in a region in which the metric does not depend on U, for instance, the asymptotic far future or the asymptotic past, in which these functions are just constant, this term drops out. So you only have a shift essentially of your waveform. Yep. Yes, this thing, exactly. So if you are in a region in which the CAB, so, okay, now the notation is a bit overwhelming maybe, but essentially a CAB is the coefficient of R in the boundary coordinates of the boundary angular components of the metric. Since this guy goes like 1 over R in mu nu, namely Cartesian or Minkowski indices, when you go to boundary coordinates, you get a factor of R for each angular index, essentially. So essentially what I'm trying to say is that the angular components in boundary coordinates of this guy indeed go like R. So this is the right component we are looking at. Now, if you're looking at a region of your waveform which does not depend on U, particular for large U, the theta function does not depend on U, it's just a constant, right? So then this derivative of U acts trivially. So that was, yeah, what I was trying to say. And well, this was the exercise I gave to you yesterday, so I'm not going to redo that. What I'm going to do is to show that this function here that appears inside the memory effect actually is, in a sense, a pure super translation. So there exists a T such that the ADB minus 1/2 gamma AB Laplacian of T is precisely that function. And this was realized essentially by Strominger and Giboido back in 2014 and recently rediscussed in a paper by Veneziano Vilkovisky in 2022. which is relatively clear. So essentially the exercise I wanted to do is to calculate dA dB minus 1/2 gamma AB Laplacian of 1 minus n hat dot v, where v is a velocity, spatial velocity, and then times log of 1 minus n dot v. So the idea is that, of course, you can also rewrite the Weinberg, let's say the structure in the Weinberg factor pi pj divided by pi dot n as, okay, there will be a gamma factor, or let me call it sigma, right? The spatial vector is equal to the velocity times the mass times the spatial, times the gamma factor, right? mj vi vj divided by vi dot n. So this is the function that we would like to get. If what I did, if the guess for this function is correct, we should get this thing. Sorry, e minus ej minus ej minus n dot. This should be it. Let me write it more clearly, otherwise it's invisible from up there. Okay, in order not to make confusion between E and I, E and J being spatial indices, I'm going to use that now, and E and J being the particle indices, let me just not put any index here, otherwise it becomes a bit confusing. Sorry about that. Sorry, P, I, J, now are the indices for spacetime, E minus N dot K hat, and this should be VI, VJ, divided by 1 minus n dot v, and then a sigma and a mass. That should be the statement. Very good, so let's do this. To do this, I need to recall a couple of rules that are very nice and you can prove essentially by going back to your early differential geometry and GR courses and doing the change of coordinates from Cartesian to spherical coordinates. And using this, you can prove this identity, which is very useful. So n now is going to be for me this n hat, and we are going to use I and j for I, j, k for the spatial, so three-dimensional one, and I, for instance, I going from 1 to 3. Well, the components of n hat I are all satisfy this identity, where gamma is with the metric on the sphere. So in particular, it means that they are spherical harmonics with L equal 1, right? Because this can be written as minus 1.2, 1.2 or 1 plus 1, right? So L times L plus 1. But this is just a side remark. So using that identity, it's relatively straightforward to evaluate maybe let me give a name to this guy. It's relatively straightforward to evaluate big F, capital F. So let me first do the derivative acting. Maybe let me find a bigger chalk. So when I act with the first derivative, I just have an n here and an n here. So let me do first the first n minus EB, right? Because the derivative of n is just E by what I defined. Log of 1 minus n dot v. And then when you take the derivative of the log, of course, the log cancels this factor, this overall factor, so you just get minus EB dot v. And then the fun begins when you act with the second derivative, because then you will pick an n from here, which will give a dA, but you can also use this identity here, which of course you can also rewrite in this way. So let's do just that. So we get a gamma AB from each time I act on EB and EB here, and just n dot v from the first one log 1 minus n dot v plus n dot v. And then we get a term that doesn't have gamma, which is essentially already smells like the right thing that we want, right? One minus n dot v, right? This is when we act on the log again. Now, to calculate big F, I have to take the trace of this and subtract it to the original expression with a factor of 1/2. And lo and behold, essentially by construction, the things with the gamma cancel out, right? Because the trace of gamma is 2, 1 over 2, the trace of gamma is 1, and therefore we are left with this guy here. One minus n dot v. So this would be just this guy here. Then, as I said, once we already with the gamma would cancel out. So we are just left with the trace of this guy, right? Minus 1/2 the trace of this guy, which you can also rewrite by summing over AA. This is just the absolute value of the projection of v along the sphere, right? So it's just v squared minus n dot v squared. This is not very important. You could also keep it formally like EA dot VV. Squared and gamma AB. Is there a square? I'm not entirely sure. Yeah, there should be. Not entirely sure about the square, though, I have to say. Anyway, the important bit is essentially this one, right? Because this is already looks like the projection of this on the sphere. The only thing that we need in order to make contact with the precise expression is that we have to do this transverse traces projection once and for all. So pi mu nu rho sigma, you can show that you can reduce it to a purely transverse, purely spatial, matrix by judiciously choosing this reference vector that we had. So since we chose k mu to be omega 1 comma n hat, you have to choose this guy in order to satisfy the identity lambda dot n equal to -1, lambda dot k is equal to -1 and lambda squared equal to 0, which means that it should be 1 over 2 omega 1 minus n hat. So using this choice, this is your, let's say, your transverse projector, and therefore your transverse traces projector is built out of this guy, and you should be able to check that the transverse traces projection of this thing is precisely this thing, in the sense that EIA, EJB, pi IJKL of VI, VJ, let me not put the denominator since I'm a bit confused about this factor here, sorry about that, is precisely EA, let's say EA dot V, EB dot V minus 1/2. Yeah, I think there should be none. V squared minus n dot V. Anyway, I invite you to double check, but this is, and then there is the denominator which already appears, so we don't have to do anything to this guy here. So anyway, this shows that there exists a function, and we explicitly check this function over here, that satisfies the following property, that it's, when acted upon with this super translation operator, it gives precisely one piece of the Weinberg factor. So then, of course, you can add or subtract as many of those as you want for each of these particles. So let me write it down explicitly over there and comment. So to summarize, the statement is the following, that our HAB induced by a memory effect, which is again E Gij, essentially, minus eta ij, or Hij, as I called it, is just R for G. And then, in principle, you can rewrite all these factors as dA dB minus 1/2 gamma AB Laplacian of sum, so theta of U, sum over the incoming states, minus n dot Vj log of minus n dot Vj, where j is the index running over the in states, sorry, the out states then. Yeah. And then the one with the plus, the one running over the in states now. Dot Vj log of minus n dot Vj, where I introduced this Vj to be the, you know, the velocity, the covariant for velocity, right? So it's, this guy is gamma or sigma j, Vj, mj. No, sorry, without any sigma here. You can check that multiplying by sigma this identity we proved, it remains exactly the same. Essentially, precisely because n, which is the guy appearing here, is in the kernel of the Laplacian. I mean, it's an eigenvalue, an eigenvector of the Laplacian, as we showed. And then, so this would be the result that we derived earlier on, just rewritten using this identity. So we done nothing. But in principle, if you want to do a super translation, you can do it, and you can do it however you want, right? So plus R for G, and then, I mean, J running on whatever, running over all the particles and some arbitrary parameter, xj, and then again, minus n dot Vj log of minus n dot Vj. So this is the general, let's say, the most general formula of the memory effect up to a super translation. You can pick however you like, and then now we should be in a position to see what I was trying to say earlier in words. So, for instance, you can set all xi, all xj's to 0, and then you are just with the formula that we had earlier, with the sum over out particles in the far future and the sum over the in particles in the far past. But if you want, you can choose xi to be just 1 if I is maybe minus 1 if j is in and 0 otherwise. In this way, you will simply kill this term from here, and you will get a theta of u, the difference between sigma out and sigma in. So in this way, maybe let me write it down pictorially, you get a waveform that looks like this. It goes to 0 for minus infinity, and it asymptotes to sigma out minus sigma in. Sum over out minus sum over in. So again, the memory effect hasn't changed because, of course, the difference between plus infinity and minus infinity is still sigma out minus sigma in, precisely as it was earlier on. But we have changed the precise value of the shear as we go, so of this HAB, as we go to, for instance, to minus infinity. Now it tends to 0, whereas earlier on it tended to something that depended only on the incoming states. So what we have shown is that the memory effect is super translation invariant, and it was already obvious from what we said earlier, but in principle, the precise value of the shear is super translation dependent. So the question now becomes, is there an observable, not the memory apparently, but is there an observable that is sensitive to the precise value of the shear, to what constant it asymptotes to in the far past, say, or in the far future? So this is a good time to stop and ask for questions, if there are any. In the meantime, I can start erasing slowly from this black part. Yeah, so maybe let me erase this one. Okay, maybe since I'm a bit quicker than I expected, maybe let me actually recall very quickly the proof of this identity that I used. I think mathematicians have a name for this identity, like Euler's something, but I don't remember exactly. So the idea is that if you start from flat space, so Cartesian coordinates, you can write down, of course, that 0 is equal to di dj x, let's say k, for instance, right? Simply because xa becomes, the derivative of xk is the delta of kj, and therefore it's a constant. And now, of course, since this statement is true in Cartesian coordinates, you can also write it down in terms of covariant derivatives, because the Christoffel symbols are all 0 in Cartesian coordinates, right? Now, of course, you can, since now you have an identity that is true for covariant derivatives for each fixed k, right? Treating the collection of the 3 components of xk as functions. Now you can write this identity in any coordinate system that you want, in particular in spherical coordinates that you can introduce by saying that xi is equal to r n hat I, right? And, okay, I will not derive for you the Christoffel symbols, but trust me that the Christoffel symbol that we need is this one. Now, of course, n is a function of some xa variables that are our angles. Let's say xa could be theta and phi, for instance, or some other more exotic variables that you want to choose on the sphere. And, okay, this Christoffel symbol is precisely minus r, the metric on the sphere. And now we can write down this identity, but in looking at the angular component in the new coordinate system. Again, k is treated like a fixed index. So now you have essentially 2 options. One is when this, of course, there will be Christoffel symbols of the type gamma c a b that are associated to the connection on the sphere itself. So all these indices live already on the sphere, but those are just those that you need in order to reconstruct the covariant derivatives that we used throughout, right? These are the ones that define what this d as opposed to del actually meant. And the new piece is the one that comes from, the extra piece that comes from the embedding of the sphere inside the 3-dimensional space is precisely minus r gamma a b. And, well, if there is a minus, then here is a plus, of course. And dr of Rnk, but of course the derivative simply acts trivially, and then you get this identity. Let's say it will be plus gamma ab n equal to 0. This is a cute proof, I think, of this useful identity that is, because as you can imagine, working directly on the sphere is in principle conceptually more straightforward, but in practice is a bit tedious. So identities of this kind that you can deduce by embedding the sphere in some higher dimensional space are actually very useful. For instance, all the multiple decompositions that people do of these waveforms, whereby you decompose your transverse traceless waveform, let's say ij, into multiples, like you have a leading order multiple that does not depend on the angles, then you have another one which is ijk, nk. So people essentially in this business don't use the spherical harmonics which are intrinsic to the sphere. They actually use nks and powers of these nks. For instance, u1 over n factorial, I think, uijk, etc. And let me not be very precise, but contractions of completely symmetric tensors that do not depend on the angles times n are very useful, in particular in the post-Newtonian decomposition. And in order to manipulate those, you need this identity. So that's why I wanted to emphasize it a little bit. Okay, so now mass aside, let's go on with our program, right? Which was, now that we have an iconal operator that provides us with a description of the final state for the collision, not only about an in-cause information, not only about the deflection, but also about the soft, at least, part of the spectrum, we can calculate observables associated to the gravitational waves. This is the soft waveform, or if you want, in time domain, the asymptotic value of the waveform in the late and far, in the late future, in the far past. Another observable that we can insert is the energy momentum. So on this, let me make a remark. Of course, the most straightforward way to write this down would be integral over k, which I remind you is a shorthand for the integral over the graviton phase space, k mu, a dagger I, ai, summed over I from 1 to 2. Let me not spell out the sum explicitly. I mean, equivalently, since eventually we are going to evaluate this on the expectation value of this guy in the final state, in which we only insert physical gravitons. You remember, in the form of the iconal operator, only the physical gravitons were put. You can actually put any gauge that you like. For instance, you can evaluate this in the Donder gauge, where this takes a relatively where you don't have the sum over physical polarization explicit. You treat all the components of the graviton as if they were independent, like in Feynman gauge, right, in electrodynamics. Where this is a constant tensor, is the constant tensor that appears in the de Donder Lagrange, right, after you subtract out the gauge fixing piece. So this is just a remark for the moment. We can use this formula if you like. Then what we want is this guy here, the expectation value of P, let's say P alpha, in the final state. Now, in principle, I should write down again okay, let me remind you the form of the iconal operator, at least schematically. This is e to the integral w a dagger minus w star a. And now what happens is, again, that using the Baker-Camper-Hausdorff formula that we recalled earlier, each a pulls down the coefficient of a dagger and vice versa, and then in addition you have this k mu. So you have the integral on k, and then there was, okay, this is integral on k up to omega star. Now it's important because you don't have any u to send to infinity in order to stick to small frequencies. You have to remember to put the cutoff by hand. So there would be, again, w mu nu pi mu nu rho sigma w rho sigma, right? And probably a star somewhere, maybe on the right. Here the star is irrelevant because you can always choose real polarizations. And the I epsilon does not play any role, as we will see momentarily. And this, okay, let me make this star explicit by writing down the theta function. But now again, I can use the useful property of this W, which remind you are, perhaps I didn't emphasize it enough, in fact. These W satisfy this identity, right? They are gauge invariant by themselves. So when I insert this pi, mu nu rho sigma, you can use the formula that I showed you earlier and substitute this guy with the de Donder structure, which does not depend on any reference vector, and it's just simple constant contractions, plus pieces that have at least one k mu or one k nu or one k rho, one k sigma, which, however, all vanish thanks to this property. I mean, this is, of course, let me this is clear that it's satisfied by momentum conservation, right? Because when you contract this K, say, with this guy here, they cancel the denominator, and then you get the sum over pi nu, which in my convention sum up to 0 by momentum conservation. So this is an important fact. Very good. So this is the idea of the calculation. You can substitute this with integral over k, k alpha. Essentially, you get w mu nu minus, okay, 1/2, because we are in 4 dimension. This is an observable which is finite in 4 dimension. W mu nu eta mu nu squared. Now, the only tricky bit now is that, of course, this integral is formally from 0 to a cutoff omega star, but the information is equivalent, right? This would give, if this is omega, and this is dE over d omega, let me consider the 0 component, or so the time component, which is the energy, of course. So this would be this bit here. Right, so of course, since we only trust this formula for very small omega star, this information is equivalent to giving the value of this d omega at 0 frequency, right? So what we really can trust is the so-called 0 frequency limit of the energy spectrum. Which, by the way, is also in papers by Weinberg back in the days. Although he was mostly focusing on the PN approximation. Instead, here today we are for generic velocities. So, okay, just to be very precise, this is the derivative with respect to omega star of minus T alpha T alpha being the, it's basically 1, 0, 0, 0 in your preferred reference frame. So it's just a convoluted way of saying the 0 component. And this I'm going to call, and this evaluated the omega star equal to 0. Let me denote it like this. So essentially, I didn't want to spell out this calculation in detail because I thought I would be late. Instead, I'm earlier, so in principle I could do that, but unfortunately, I don't have it in my notes in very great detail. But the idea is the following. Now, you insert this into here, and what you get will be contractions with p that are actually constant. They don't depend on the k that is integrated, right? So the only non-trivial integrals are integrals of type 1 over pi dot k, 1 over pj dot k integrated over k. So let me give you that integral. So if you want to do this, you can. So the integral from 1 over, maybe let me introduce, of course the mass can be factored out from this denominator. You just redefine p mu in terms of the mass and the velocity, like I did there. So let me write it down again. V mu n is equal to eta n pn mu divided by the mass. So the non-trivial integrals are of this kind. Vn dot k, Vm dot k. And essentially for any pair Nm, the trick to do these integrals is to go to sort of the center of mass frame of particle n and particle m. Of course, they can be general, because this formula applies for generic n to m processes. But for instance, when you pick particle 1 and particle 2, this is really the center of mass frame of the incoming particles. But you can play a similar trick to calculate the integrals for particle 1 and particle 4, for instance. This is a very instructive exercise. And the result is the following. I mean, the integral is formally divergent just because it's scale invariant. But again, we only trust this for small frequency, and then we need in any way to take the derivative at the end. And there's a 2 pi squared, sigma squared nm minus 1, where sigma nm is the analog of the sigma that we had yesterday, but for particle n and particle m. This is the type of integral that you land on. It's very easy. In the end, you reduce yourself to an integral that is that you can reduce by partial fractions, just like the integral of the box that we had at some point yesterday. And in fact, you recognize the same arc cosh divided by square root of x argument squared minus 1, which also appeared in yesterday's calculation. And, okay, using this expression, the final result for the e over the omega is the following. Sorry, sigma squared n. This comes from the structure here appearing in the Donner propagator, right? Because these guys will induce contractions between pi and pj with different I and j, whereas here you will get the trace essentially, which is this minus 1/2 here. And this is also reminiscent of what he had earlier in the iconal phase, which was like sigma squared minus 1. That minus 1 also comes, minus 1/2, which also comes from the structure in the Donner propagator. It's essentially associated with the fact that you are subtracting out the exchanges of dilatons in the intermediate calculation. There is no dilaton in GR essentially. Arc cosh divided by square root. Okay, so I wanted to write down this explicitly because now we are in a position to comment on a small paradox that I mentioned yesterday very quickly, which has to do with the high energy limit of the behavior of this post-Minkowskian approximation that we have been using in the high energy limit. So you remember at the beginning we were saying, well, this post-Minkowski approximation is more general than the post-Newtonian one because we are not restricting to velocities small of the order such that v squared is of the order of gm over b, and this is true. And, okay, without spelling it out explicitly, we were saying, so therefore it means that it's valid for arbitrary velocities. This is not entirely correct, and essentially in this formula, you can already see to some extent why. So these sigma and m are very similar to the sigma we had yesterday when, okay, let me now specialize to the 2-to-2 process again, just for concreteness. So for instance, sigma 1, 2 is really sigma, so it's p1 dot p2 divided by m1, m2. Sigma 1, 2, which is what yesterday we were calling sigma. And similarly, you can check that sigma 3, 4 is essentially sigma plus or minus, now I don't remember exactly, but q squared over a factor of m squared. Now, in the limit in which the energy becomes very large, sigma becomes essentially proportional to the momentum, so this factor is indeed small, provided that the theta is small. So this is the sigmas. So what I wanted to say, let me not spell it out very explicitly because the factors might be slightly incorrect, but the idea is that the sigmas with 1, 2 and sigma with 1, 3, 1, and 2, 4 are not problematic in the high energy limit. What the interesting bit is the interesting bit of this formula is when the sum is over, let's say, 1, 4, and similarly for 2, 3. Essentially, in that case, you will get an arc cosh of 1 plus q squared over 2m squared divided by the square root of the argument squared minus 1. So this comes from this arc cosh. And now you see what the tricky bit is, right? That for high energies or for small masses, it depends what you do exactly with this factor here. So when this factor here becomes too large, you might start hitting one of the branch point that this function has in the complex plane, and therefore the approximation for small q, which is the post-Minkowskian approximation, might break down. Let me be a bit more precise about that before we move on to the angular momentum. So the PM approximation would be q smaller than m, essentially, right? Small deflections compared to the masses. And in this regime, this formula, this function is well behaved. However, in principle, if you want to take the high energy limit, you remember, to leading order in the PM approximation, at least for small deflection, q is of the order of p times theta, p the momentum, which itself can be rewritten as essentially m1, m2 divided by 2, theta, the square root of sigma, right? This comes from that formula that I asked you to prove yesterday, m1, m2, square root of sigma squared minus 1, and the fact that E itself is m1 squared plus 2 m1 m2 sigma plus m2 squared. So for very large sigma, E is essentially 2 m1 m2, and this tends to m1 m2 sigma. Right, so we are now taking the high energy limit. Sigma going to infinity. And therefore, since this function here has a branch singularity for, okay, formally q squared over 2m smaller than minus 2. Of course, this is outside the regime, I mean the physical region. This is just a statement about this function as an analytic function in the complex plane. There is a branch cut. This can be almost seen by naked eye in the sense that, sorry, arc cosh. The arc cosh of 1 becomes 0, and then for arguments smaller than 0, the arc cosh is not well defined. So it has a branch singularity. However, that singularity is cured by the square root sitting in the denominator. The branch cut actually starts when you hit minus 2 instead of minus 1, right? Which would be the thing making this argument 0. This is just a detail. Anyway, this function has a branch cut, and therefore we know that the series, the PM series for Q much smaller than M, must have a finite radius of convergence, which is precisely dictated by this singularity. So in particular, by comparing these two, you find that this bound, so that the PM series converges for sigma big in general, because theta is small in the PM approximation, but not arbitrarily big, right? For sigma smaller than 1 over theta squared. In fact, this is a bound that had been pointed out back in the 70s in different contexts. So it's known in the context of studies of gravitational waves. In particular, it comes from the analysis of some collinear regimes in explicit expressions for waveforms at the leading post-Minkowskian order. But somehow this is I would say that this is proof of this fact. So okay, you have to be careful because some observables, in particular some radiative observables, might be ill-defined if you go to too high energies. Okay, so now let me move to the last topic. Which is angular momentum. So again, the logic is always the same. We have our Iconal operator. We can insert whatever observable we want. In particular, if we want to study the angular momentum of the gravitational field, we have to insert the angular momentum operator of the gravitational field, which, okay, now I write it down in the Donder gauge, as I was anticipating a little bit with the discussion of P alpha over there. So this is the expression. By the way, I think the expression for P mu in terms of oscillators, like in the Fock space, is rather standard, right? You find it in most textbooks. This one is a little bit, I guess, less standard. Of course, the logic of the derivation is very similar. Write down the Noether charge associated to rotations and boosts instead of translations. You insert the canonical quantization of the field as you learned in first or second year of master, and then this is the expression that you get. The only tricky bit, of course, are these derivatives, which make your life a bit harder. So this is let's say, less trivial exercise. It's done in great detail in some lecture notes by Professor Soldati from Bologna that you can find online, I think, freely available online. So there it's discussed in great detail. This is really the canonically quantized with flat background graviton field. So in principle, it's a textbook calculation. The point is that it's not in any textbook that I know of. Precisely. Precisely. The only step, in addition to the one that, for instance, you teach in your course, I think, is that then you substitute the canonically quantized field, and then you work out the expression in terms of A and A dagger.
Do you really need the canonical computational relation, or just to substitute the Fourier transform?
It's basically just a Fourier transform, yeah. There is probably something related to, we have +1/2 or -1/2, the commutator and the anti-commutator, so, but that's only probably the vacuum, whatever, that you also have in the energy for the canonically quantized scalar, for instance, right, for the energy. But that's not the bit that we are interested in here, yeah. So now what we want to do is we want to insert this in the final state and calculate this object here, right? Again, the idea is that A pulls down A dagger, the coefficient of A dagger. Yeah? Please.
This is really the canonical one or the belief factor one?
So this is the canonical one, yeah. At least I did it with the canonical one. And this is the result that you get.
The symmetric? The canonical one, I would say, is not symmetric.
Yeah, somehow it's, I don't think it really matters, right? Because here it's really integrated on a Cauchy surface. Yeah, this is also the expression in the Donder gauge, but no, it doesn't matter, because it's really J mu d sigma mu, right? So, yeah, so you really integrated mu. Okay, no, I never did it let's say, I never compared the two, but yeah. Very good. So this would be the idea. Of course, again, this is made a bit trickier by the fact that there are derivatives in the meantime, in the middle, right? So, of course, when you pull down, for instance, from there, this A pulls down the coefficient of A dagger, which has a W, which in its turn has the projection over physical, has the polarization. So you might be tempted to just write down the following formula. Minus I, and then here, let me give an A to the structure that appears in the de Donder propagator as opposed to the, okay, let me write it like this. Then I will explain. So, as I said, W is pulled down by A dagger, W star will be pulled down by its partner, and then there is plus 2 W. So here there are no derivatives. This is essentially the spin term, right? This 2 is the spin of the graviton. W star, W beta, mu. Where if I put no indices now, I mean W star mu nu, eta mu rho, eta nu sigma -1/2, eta mu nu, eta rho sigma, W rho sigma. So the contraction with the structure appearing in the de Donder propagator, because as we saw when we project over physical polarization, there is the de Donder propagator plus bits that contain K mu, and therefore vanish when contracted with W by this property here. Now, what makes the step not trivial is that some of these derivatives actually kill the K mu appearing in the projection. So it's not entirely obvious that you can go from here to here, but it's actually true. So this is another instructive exercise that I'm not going to do on the blackboard, but it's non-trivial. Another thing that you can check in order to convince yourself that this step is not trivial is that gauge invariance is not entirely manifest, right? Because again, when you, from this formula here, if you, for instance here, when you send W to W plus, let's say, xi mu k nu, it's obvious that the result is invariant because Okay, again, a k nu will always contract the other w, right, in this substitution. However, here it's not obvious because there is a derivative that can kill 1 over k nus. So you can check that actually only the sum of these two is gauge invariant, and the terms spawned by this guy under the gauge transformation are killed by analogous terms that are spawned by this guy, in which some of the k's are not contracted. You see, they appear with free indices. So gauge invariant with an exclamation mark because it's not entirely trivial. Moreover, I mean, this should sound reasonable because whereas here there is a distinction between spin and orbital angular momentum that is gauge invariant because they are separately gauge invariant in the sense that they are both contracted with the physical polarization appearing in W. Here there is none, so these two are reminiscent of orbital and spin angular momentum, but only the sum of the two is in this case manifestly covariant and gauge invariant. Very good. So now, okay, luckily, the integrals that we have to do in principle to go to the final result are almost the same as the ones that we had earlier. Okay, there is a derivative which will give some power to one of the two guys appearing up there, but this is not really an extra difficulty. The only difficulty that I wanted to discuss a bit more in detail is the role of this star, which now is actually crucial, right? For instance, in this term, you can clearly see that if it weren't for the star, it would be clearly zero, because it's the anti-symmetrization of the contraction of something with itself, which is symmetric. So this tells you that the result will be manifestly imaginary, which makes sense because the observable must be real. But where does this I come from? Well, it should come, it's no surprise that it comes from the I epsilon prescription. So essentially the integral that I did for free here, it's an integral from 0 to omega star of some power of omega that gives this omega star to the minus 2 epsilon, now becomes essential, so I need to discuss it separately. So the integral is still scale invariant in d equal 4. So the reason why I had to stay in d slightly away from 4 here, before taking the derivative with respect to omega star and sending omega star to 0, was that this integral is scale invariant, right? Because you have from the measure, you would have a delta k squared and d 4k, right? Delta k squared counts as minus 2 because delta is homogeneous of weight minus 1, so it's 4 minus 2 minus 2, which is 0. So the integral would have been strictly scaleless in d equal to 4 and therefore divergent. Now the magic that happens here is that you land on this integral here. The omega, and then they have again to be careful about the sign of Pn, if it's Pn is incoming or outgoing in the sum over n, minus or plus I0 because this is the one appearing on the left, and minus I0. So this is just the integral over the frequency. The integral over the angular part is exactly the same that you have in the energy case and lands on this arc Koch, which will also appear in the final result. The integral that we have now on the relative frequency is this one, which, as you can see, is also scale invariant, right? Because it's omega divided by omega. But the magic of this I epsilon prescription is that it's actually finite, and it's equal to minus I. Okay, maybe let me be a bit more precise about the order of limits because it can be a bit confusing, right? Here is a limit which is the small epsilon, right? The small 0 here, and also omega is a small cutoff. So what I mean by this expression is that it's the limit for small cutoff performed after the limit, let's say, of small lambda or small epsilon if you want. Of course, one of the two must be an m. Apologies for that. Yeah. So, of course, this is an integral. It's a trivial integral. You can do it by partial fraction. It will give some log and some rational piece. So you can do that and then take the limit lambda going to 0. This will give an I pi that does not actually depend on omega from the branch cut of the log. And the result is simply minus I pi over 2 eta n minus eta m. So you see that it is crucial that there are some incoming and some outgoing particles, because if I only add all outgoing particles, this integral will be trivially zero, and then there is a companion integral that you have to worry about at some point, which is very similar. Minus. So the one with the squared, essentially, which is also minus I pi, the sign of this particle. So these integrals are, I mean, somehow show why sometimes you have to care about the epsilon prescription. And okay, using this plus this, you can massage your way from that expression to the final result. I wanted to write here and then comment. Yes? No, it's important to interpret it in this way, which is, I guess, the physically correct way. In principle, you evaluate the angular momentum for some bin of frequency. And okay, the I epsilon prescription is just there to remind you how you defined your amplitude to begin with. And then, okay, you can take the cutoff to zero at the very end, because as you can see, it does not depend. And as you can see, you still get a finite result. So, okay, the expression is the following, and I'm concluding more or less in time, I think. So this JAB is the sum, so minus sum over n in the in and sum over m in the out, sum C and M, Pn alpha, Pm beta, with C and M equal to 2G sigma squared Nm minus 1/2, which is the usual structure that comes from the de Donder structure in the de Donder propagator, some delta that I'm going to define in a second. Minus 2, which comes from the spin term, essentially. The spin term is easier because it doesn't have any derivatives. So it's actually the same calculation that we did earlier with delta, this arc cosh that we had. Very good. So now 2 comments before concluding. Well, the first one is that since it has the same sigma and m that appeared earlier on, right, there is also in particular a sigma 1,4, which is that 1 plus q squared over 2m squared, etc., etc. So the same issue about convergence of the post-Minkowski function also applies to the angular momentum. This thing is well defined only below the threshold sigma smaller than 1 over theta squared, essentially. However, the formula is valid also above, and just like for the energy spectrum, it provides you with the correct behavior also above, if you refrain from doing the small q expansion, of course. And you can see that the reason for this breakdown of the post-Minkowski approximation is the fact that there are some logs. So in particular, if you first do the high energy limit or the small mass limit and then take sigma to be small, you see that the behavior is not, I mean, it does not tend to infinity. It's just some log. It behaves like logarithm of the theta angle. And somehow the reason for this breakdown of the approximation is that you were trying to calculate the coefficient of g, or of g cubed more precisely, of a function, of the series expansion of a function that does not have a power series expansion, right? When you try to expand log of x near x equal to 0, you find nonsense. The other comment is this sum over in times sum over out, which comes from the issue with the epsilon prescription I was mentioning. And okay, although I didn't discuss it in great detail, it should make reasonable to you that if I changed the waveform, which is actually equivalent to changing the I epsilon prescription in the Weinberg factor, which was minus I0 for us. If I change this by performing a super translation and I arrange the memory effect to be just 0, I mean, to the value of the shear to be 0 at minus infinity and sum over out minus sum over in the far past, in the far future, essentially I super translate this whole formula to 0. And the reason is that there is no, I mean, in this formula there is no product between some sigma out and some sigma in, which is crucial to get some different epsilon prescription. It's just some sigma out minus sigma in times 0. So you get no such effect at all. So okay, the interpretation of this fact is still a bit debated in the literature. I mean, my personal view is that okay, general relativists have tried to convince us for now many years that supertranslations are physical transformations, so there is nothing to worry about. I mean, just like angular momentum and momentum can depend on rotations, translations, which are of course physical symmetries. Okay, this is, is an observable consequence of the supertranslation frame you're sitting in. Of course, supertranslations are a bit more subtle to interpret, I mean, intuitively than standard translations and standard boosts, etc. So people have different viewpoints. For instance, there are other people that instead endeavor to find definitions of momentum, or angular momentum, that are different from the ones we use here, and have to do with the expansion of the field, massage in different ways. Let me not be precise about that, but essentially it's involving that angular momentum aspect that Andrea had in one of his lectures, and different versions, different flavors of how that can be used to define different versions of the angular momentum itself, and people come up with definitions of angular momentum that do not depend on supertranslation at all, and eventually reduce to the one I gave here for the 2-to-2 scattering process that we are interested in. But okay, this is an open problem, and I thought it was nice to end with some food for thought. So thank you for your attention.
If you have quick questions, please. In any case, today, 2:30, we have our Q&A session. So agree to reconvene at 2:30 after lunch and break. Okay. Thanks again, Carlo.